Hello everyone, I already discussed about basic thermodynamic processes and basic thermodynamic relations in previous video. Let us today discuss about basic equations of compressible flow. That includes continuity equation, Bernoulli's equation or energy equation, momentum equation and equation of state. Now let us first discuss about continuity equation. So this is based on law of conservation of mass, which states that matter or mass cannot be created nor be destroyed, or in other words the matter or mass remains constant. So we can apply this concept for one dimensional steady flow. The mass per second, that is represented by m dot, it is given by m dot equal to rho av, where rho is the mass density, or simply it is a density, a is cross sectional area, v is flow velocity. As mass or mass per second is constant according to the law of conservation of mass, hence rho av equal to constant. Now just differentiate above equation. So we are going to get differentiation of rho av equal to differentiation of constant. As we all know, differentiation of constant is equal to 0. So we get differentiation of rho av equal to 0. Apply product rule for rho av, taking rho as first term and av as second term. So we get rho into differentiation of av plus av into differentiation of density equal to 0. So you can take outside rho and again apply product rule for av, that is area into velocity. So we get rho into adv plus vda plus av d rho equal to 0. Or you can just multiply rho inside the bracket, we get or rho a dv plus rho v dA plus av d rho equal to 0. So dividing entire expression by rho av, we get dv by v plus dA by a plus d rho by rho equal to 0. Above equation is known as continuity equation in differential format. This is very important equation. Next, let us go for Bernoulli's equation. But about Bernoulli's equation, we are going to study in third module, that is laminar and turbulent flow and fluid dynamics. For time's sake, let us just write down the expression as dp by rho plus v dv plus g dz equal to 0, where p is pressure, rho is density, v is velocity and g is acceleration due to gravity and dz is difference in elevation. So integrating above equation, we get integration of dp by rho plus integration of v dv plus integration of g dz equal to constant. So upon simplification, we get integration of dp by rho plus v square by 2 plus gz equal to constant. As integration of v with respect to dv, that gives v square by 2, and integration of g with respect to dz, as g is constant you can take outside, so we get g into z. So overall expression becomes integration dp by rho plus v square by 2 plus gz equal to constant. This is a Bernoulli's equation. Now let us apply this Bernoulli's equation for two possible cases. That is, one is compressible and another one is incompressible fluid. As we all know, for compressible fluid, density is not constant. Density is going to change with respect to time. So in order to differentiate or integrate first term, that is integration dp by rho, we should know the relationship between pressure and density. So for in compressible flow, expression becomes dp by rho, integration dp by rho plus v square by 2 plus gz equal to constant. But for incompressible flow, as we all know, density remains constant, so rho equal to constant. So you can take 1 by rho as constant from integration sign. So 1 by rho into dp, integration dp plus v square by 2 plus gz equal to constant. But integration of dp is p, so we get p by rho plus v square by 2 plus gz equal to constant. So upon simplification, p by rho plus v square by 2 plus gz equal to constant. Now we can apply Bernoulli's equation for two important processes, that is isothermal process and adiabatic process. We all know about isothermal process, where temperature remains constant. So for characteristic equation for isothermal process is given by PV equal to mRT, that is equal to constant, or you can simply write PV equal to constant. So we can rearrange the expression PV equal to mRT, that is P into V by M equal to RT equal to constant, but M by V equal to rho. So here we have V by M, that is reciprocal of density. So we get P by rho equal to constant, say that is that constant equal to some C1. So but from Bernoulli's equation, we have integration dp by rho plus v square by 2 plus gz equal to constant. take that expression as 2. Now you can substitute from equation 1 rho equal to P by C1 in 2. So substituting in 2, that gives integration dP by P by C1. In place of rho you are supposed to substitute P by C1. So we get integration dP divided by P by C1 plus V square by 2 plus Gz equal to constant. So we can take C1 to the numerator. So integration C1 dP by P plus V square by 2 plus Gz equal to constant. Now C1 is a constant, so you can take outside the integration sign. So C1 into integration dP by P plus V square by 2 plus Gz equal to constant. But integration of 1 by P with respect to P is ln of P. So C1 ln of P plus V square by 2 Gz equal to constant. But from equation 1 we have C1 equal to P by rho. So just substitute in place of C1 P by rho. So P by rho ln of P plus V square by 2 plus Gz equal to constant. Divide entire expression by G. So that gives P by rho G ln of P plus V square by 2G plus Z equal to constant. So we can apply this expression for 2 points, state points 1 and 2. So that gives P1 by rho 1 G ln of P1 plus V1 square divided by 2G plus Z1 equal to P2 by rho 2G ln of P2 plus V2 square by 2G plus Z2. This expression is very important for problem solving for our isothermal process. So just remember this expression. Now let us go for adiabatic process. As you all know, adiabatic process is a type of process in which there is no heat transfer from system to surrounding or surrounding to system, that is Q equal to 0. The characteristic equation is given by P divided by rho to the power K equal to C2. In order to avoid confusion, you can assume constant T as C2 because we already use C1 in isothermal process. So from this we can get rho to the power K equal to P by C2. You can get expression for rho as rho equal to P by C2 to the power 1 by K. Take that expression as 1. But from Bernoulli's equation we have integration dP by rho plus V square by 2 plus Gz equal to constant. Take that expression as 2. Now substitute 1 in 2. In place of rho you can substitute P by C2 to the power 1 by K. So integration dP divided by P by C2 to the power 1 by K plus V squared by 2 plus Gz equal to constant. Now you can rearrange or you can apply the power to numerator and denominator term. So we get integration dP divided by P to the power 1 by K divided by C to the power 1 by K plus V square by 2 plus Gz equal to constant. So C to the power 1 by K you can take to the numerator. So integration C to the power 1 by K dP divided by P to the power 1 by K plus V square by 2 plus Gz equal to constant. Now C to the power 1 by K, as this is a constant, you can take outside the integration sign. C to the power 1 by K integration dP divided by P1 to the P to the power 1 by K plus V square by 2 plus Gz equal to constant. So C to the power 1 by K, you can take P to the power 1 by K to the numerator. That time it becomes P to the power minus 1 by K. So C2 into C to the power 1 by K into integration P to the power minus 1 by K dP plus V square by 2 plus Gz equal to constant. So C to the power 1 by K. So integration of P to the power 1 by K, P to the power 1 minus 1 by K is P to the power minus 1 by K plus 1 divided by minus 1 by K plus 1. So you can simplify now. C to the power 1 by K into P to the power minus 1 by K plus 1 divided by minus 1 by K plus 1 plus V square by 2 plus Gz equal to constant. Now you can rearrange C to the power 1 by K, P to the power 1 minus 1 by K divided by 1 minus 1 by K plus V square by 2 plus Gz equal to constant. So C to the power 1 by K, you can take the LCM here. So P to the power K minus 1 divided by K minus 1 divided by K plus V square by 2 plus Gz equal to constant. Now you can rearrange C to the power 1 by K into K divided by K minus 1, P to the power K minus 1 divided by K plus V square by 2 plus Gz equal to constant. But from expression 1 we have C2 equal to P by rho K. So you can replace C2 by P by rho K, rho to the power K. So in place of C2, P divided by rho to the power K 1 by K into K divided by K minus 1, P to the power K minus 1 divided by K plus V square by 2 plus Gz equal to constant. You can take outside K divided by K minus 1, K divided by K minus 1 P to the power, you can apply 1 by k to P term as well as rho to the power k term. So that time it becomes P to the power 1 by k divided by rho to the power k to the power 1 by k. That is going to cancel into P to the power k minus 1 divided by k plus V square by 2 plus Gz equal to constant. Now upon simplification, k by k minus 1 into P to the power 1 by k, you can combine together P terms, P to the power 1 by k plus k minus 1 by k divided by rho plus V square by 2 plus Gz equal to constant. Now 1 by rho into k divided by k minus 1, P to the power 1 plus k minus 1 divided by k upon taking LCM plus V square by 2 plus Gz equal to constant. Now we can take P to the power k by k is 1. So P to the power 1, P divided by rho into k by k minus 1 plus V square by 2 plus Gz equal to constant. So just divide above expression by acceleration due to gravity, that is G. Is similar to your isothermal equation itself. You have to divide entire expression by G. So k divided by k minus 1, P by rho G plus V square by 2G plus Z equal to constant. For applying this expression for two state points 1 and 2, so k by k minus 1, P1 by rho 1 G plus V1 square divided by 2G plus Z1 equal to k by k minus 1 into P2 divided by rho 2 G plus V2 square divided by 2G plus Z2. So this is an expression for two state points. So here you have to note down one important point. Instead of K, you can take it as gamma, some gamma. Constant as the ratio of specific heat. Here in this R.K. Bansal textbook, they have used symbol for a ratio of specific heat as K. So you can replace, for your convenience, you can replace K by gamma. So let us go for solving the problem. First problem, a gas is flowing through a horizontal pipe which is having a area of cross section as 40 centimeter square, where pressure is 40 Newton per centimeter square gauge and temperature is 15 degrees centigrade. So it is given clearly horizontal pipe. So that is Z1 equal to Z2. There is no difference in datum level. So and area of cross section at state point 1 is 40 centimeter square, that is A1 equal to 40 centimeter square, and pressure, that is 40 Newton per centimeter square gauge. It is clearly given, it is pressure is given as gauge pressure. You have to convert to absolute pressure by adding atmospheric pressure, and temperature, that is 15 degrees centigrade, that is T1 equal to 15 degrees centigrade. At another section, the area of cross section is 20 centimeter square and pressure is 30 Newton per centimeter square, again in gauge pressure. So A2 equal to 20 centimeter square and P2 equal to 30 Newton per centimeter square. If the mass flow rate of gas through the pipe is 0.5 kg per second, you can see the unit here, unit of mass is kg, but here it is given kg per second. There is a unit of m dot. As I already explained about this thing in basic thermodynamics, you just note down 0.5 kg per second as m dot. Find the velocities of the gas at these sections assuming isothermal change. So it is given isothermal process. So temperature should remain constant. As you can see in question, there is no T2. So that means T1 equal to T2, that is equal to 15 degrees centigrade. And take R equal to 292 Newton meter kg per Kelvin. So that is R is a gas constant and atmospheric pressure P atmosphere is given as 10 Newton per centimeter square. Okay, you are supposed to find here V1 and V2 at section 1 and 2 respectively. Now let us go for solving the problem. Before that, we can write down the given data, that is section 1 and section 2. At section 1, as I already told, A1 is given as 40 centimeter square. So SI unit of area is meter square. So from centimeter square you are supposed to convert to meter square. So this can be done like this. You can see here, in place of centimeter, 1 centimeter is equal to 10 to the power minus 2 meter. So just replace centimeter by 10 to the power minus 2 meter to the power 2. So that becomes 40 into 10 to the power minus 4 meter square. And pressure P1 40 Newton per centimeter square gauge. So again SI unit of pressure is Newton per meter square or Pascal. So you have to convert from Newton per centimeter square to Newton per meter square. Before that it is given in gauge pressure, so convert to total pressure or absolute pressure. That can be done by adding atmospheric pressure to gauge pressure. So P1 equal to P atmosphere plus 40. So 10 plus 40, because atmospheric pressure is given as 10. So is equal to 50 Newton per centimeter square, that is absolute pressure. Now convert from Newton per centimeter square to Newton per meter square. So P1 equal to 50 Newton divided by 10 to the power minus 2 meter to the power 2. So just convert, so that becomes 50 into 10 to the power 4 Newton per meter square. Don't forget to convert to Newton per meter square. This is the SI unit of pressure from Newton per centimeter square. Otherwise, you are going to end up with wrong answer. So similarly, convert temperature from degree centigrade to Kelvin. This is the SI unit of temperature is Kelvin. So T1 is given as 15 degree centigrade. That is equal to 15 plus 273. That is equal to 288 Kelvin. So that should be equal to T2 because it's the isothermal process. At section 2, A2 is given as 20 centimeter square. So convert from centimeter square to meter square. Similar, you can follow the similar step as I explained in above step. So that is equal to 20 into 10 to the power minus 4 meter square. P2 equal to 30 Newton per centimeter square. That is a gauge pressure. Convert from gauge pressure to absolute pressure. That is equal to 30 plus 10. That is equal to 40 Newton per centimeter square. Now important thing, don't forget here, you have to convert from Newton per centimeter square to Newton per meter square. So I'll write directly here 40 into 10 to the power 4 Newton per meter square, and m dot that is given in problem as 0.5 kg per second. So from continuity equation we have m dot, that's mass per second, that is equal to m rho 1 a1 v1, that is equal to rho 2 a2 v2. So now we have to find v1 and v2. So let us take individual terms, that is m dot equal to rho 1 a1 v1. So v1 equal to m dot divided by rho 1 a1, but we have values of m dot and a1 as 0.5 and 40 into 10 to the power minus 4 respectively. So just substitute 0.5 divided by rho 1 into 40 into 10 to the power minus 4. But here rho 1 is unknown and v1 is unknown. But in order to get v1, we have to calculate rho 1. So that can be done by using expression p1 by rho 1 equal to RT1. That's the equation of state. So rho 1 equal to p1 by RT1. Just rearrange the expression so that you should get rho 1 on your left hand side. So rho 1 equal to p1 by RT1. P1 is given, R is given, T1 is given. So just substitute and get the expression. So 50 into 10 to the power 4 divided by 292 into 288 equal to 5.945 kg per meter cube. Unit is very important. Unit of density is, that is density is mass by volume. Unit of mass is kg. Volume unit is meter cube. So overall unit becomes kg per meter cube. So now you have value of rho 1. So you can back substitute in V1 expression. That is V1 equal to 0.5 divided by rho 1 into 40 into 10 to the power minus 4. So we get V1 equal to 0.5 divided by 5.945 into 288, that is equal to 21.02 meter per second. So unit of velocity is meter per second. Don't forget to write the unit. Next, I have to suppose to find V2. So again take down continuity equation for state point 2. M dot equal to rho 2 a2 V2. So V2 equal to m dot divided by rho 2 a2. So m dot is given, a2 is given. Again we don't have value of rho 2. So just write down whatever the things given. So that is equal to 0.5 divided by rho 2 20 into 10 to the power minus 4. Now in order to get rho 2, again go for equation of state. So P2 divided by rho 2 equal to RT2. So get expression for rho 2. Rho 2 equal to P2 divided by RT2. So P2 and T2 and R values are known. So 40 into 10 to the power 4 divided by 292 into 288. Temperature T2 should be equal to T1 because it's an isothermal process. So temperature should remain constant. So upon substitution, we are going to get value of rho 2 as 4.756 kg per meter cube. Just back substitute rho 2 value in V2. We get V2 equal to 0.5 divided by 4.756 into 288. That is equal to 52.565 meter per second. This kind of problems are very easy to solve, but thing is you have to remember expression for isothermal process as well as adiabatic process, and you should know how to convert from given unit to SI unit, like for example Newton per centimeter square to Newton per meter square, and again from gauge pressure to absolute pressure, and temperature from degree centigrade to degree Kelvin, and area from centimeter square to meter square. That's all. So let us go for next problem, second problem. A gas is flowing through a horizontal pipe at a temperature of 4 degrees centigrade. So again it is given, horizontal pipe term is very important, that is Z1 equal to Z2. Change in datum level, that is dz equal to 0 or Z2 minus Z1 equal to 0. So and at a temperature of 4 degrees centigrade, that is T1 is given as 4 degrees centigrade. Diameter of the pipe is 8 centimeter, and at a section 1 in this pipe the pressure is 30.3 Newton per centimeter square gauge. So again pressure is given in gauge pressure. So at section 1 diameter of the pipe, that is D1 is 8 centimeter and P1 is 30.3 Newton per centimeter square gauge pressure. So you have to convert from gauge to absolute pressure. The diameter of the pipe changes from 8 cm to 4 cm at the section 2-2, where pressure is 20.3 Newton per centimeter square gauge. So diameter changes from 8 cm. 8 cm is D1. It changes to 4 cm at section 2-2. That is D2 equal to 4 cm. So next P2 equal to 20.3 Newton per centimeter square gauge pressure. Find the velocities of the gas at these sections assuming isothermal process, that is V1 and V2 at section 1 and 2 you are supposed to find, and take R equal to 287.14 Newton meter kg per kg Kelvin and atmospheric pressure 10 Newton per centimeter square. So P atmosphere is given as 10 Newton per centimeter square, and R, that is a gas constant, that's the unit of gas constant is actually joule per kg Kelvin, but joule is equivalent to Newton meter, so there is no conversion. So R equal to 287.14 Newton meter kg Kelvin. Okay, let us just write down given data. So for the section 1-1, you can write separately section 1-1 and section 2-2. Temperature T1, that is equal to 4 plus 273. So as I already told you, have to convert from degree centigrade to degree Kelvin. So that can be done by adding 273.15, or simply you can add 273. So we get 277 Kelvin as T1, and D1, that is diameter at section 1-1. Equal to 8 centimeter. Convert from centimeter to meter. Unit of SI unit of diameter is meter, so that is equal to 0.08 meter. And if you know the diameter, we can get area of cross section, that is given by A1 equal to pi by 4 D1 square. So we have value of D1, just substitute. So pi by 4 into 0.08 square equal to, we get answer 0.005026 meter square. SI unit of area is meter square. So P1 equal to 30.3 Newton per centimeter square. There's a gauge pressure. So it is obvious that you have to convert from gauge pressure to absolute pressure, because atmospheric pressure is given in problem. So that can be done by just adding 10, that is the atmospheric pressure given in problem, to a gauge pressure, that is 30.3. So 30.3 plus 10, that gives 40.3 Newton per centimeter square. There is absolute pressure. Now again from Newton per centimeter square, I have to follow the similar step whatever I have followed in previous problem. So convert from Newton per centimeter square to Newton per meter square. So I'll write directly here equal to 40.3 into 10 to the power 4 Newton per meter square. So for the section 2-2, you can follow similar step. D2 equal to 4 centimeter. Convert from centimeter to meter equal to 0.04 meter. So A2 equal to pi by 4 D2 square. So there is the area of cross section at section 2-2. So that is equal to pi by 4 into D2, that is given as 0.04. So just multiply 0.04 square equal to 0.001256 meter square. So pressure, again it is given gauge pressure. Convert from gauge to absolute pressure just by adding atmospheric pressure, that is 10 Newton per centimeter square. So 20.3 plus 10, that gives 30.3 Newton per centimeter square absolute. Now problem is not solved still. You have to convert from Newton per centimeter square to Newton per meter square. Don't forget this step. So that can be done like this, equal to 30.3 into 10 to the power 4 Newton per meter square. This is absolute pressure. You can refer previous problem how to convert from Newton per centimeter square to Newton per meter square. I explained each and every step in previous problem, so you can just refer that problem. So R value, there's a gas constant is given as 287.14 Newton meter kg Kelvin or joule per kg Kelvin. So K or gamma equal to 1.4, that is the ratio of specific heat. Instead of K, in RK Bansal textbook they have used K value as for specific heat they use K, ratio of specific heat as K. You can use gamma. In standard textbook they are going to use gamma only. So in order to avoid confusion, I have written here K equal to gamma equal to 1.4. You can use any notation. Okay, now start the problem. So problem starts with writing the continuity equation. So applying continuity equation at section 1 and 2, we get m dot equal to rho 1 a1 v1 equal to rho 2 a2 v2. Now rearrange the expression v2 by v1 in order to get v2 by v1 equal to rho 1 a1 divided by rho 2 a2. But rho 1 and rho 2 values are not known. So just keep as it is. Rho 1 into a1 and a2 we already calculated. Rho 1 into 0.005026 divided by rho 2 into 0.0012565. Upon simplification we get equal to 4 into rho 1 divided by rho 2. For isothermal process we know P by rho equal to constant. So we can apply for state points or two state points 1 and 2. So that in that time we get P1 by rho 1 equal to P2 by rho 2 equal to constant. So you just rearrange the expression because we need in V2 rho 1 by rho 2. So just rearrange above expression. Rho 1 by rho 2 equal to P1 by P2. As P1 and P2 values are known, that is 40.3 into 10 to the power 4 divided by 30.3 into 10 to the power 4. Just calculate this ratio, we get 1.333. So just back substitute this rho 1 by rho 2 or equal to 1.333 in V2 by V1. So V2 by V1 equal to 4 into rho 1 by rho 2. So in place of rho 1 by rho 2, I can substitute 1.333. So 4 into 1.33. So V2 becomes, just cross multiply V1, V2 equal to 5.32 V1. And again, applying Bernoulli's equation for isothermal process. In problem it is already specified is isothermal process, not an adiabatic process. So just write down expression for isothermal process. I already derived this expression for isothermal process. So P1 by rho 1 g ln of P1 plus V1 square divided by 2g plus Z1 equal to P2 divided by rho 2g into ln of P2 plus V2 square divided by 2g plus Z2. For horizontal pipe, as I already told, Z1 equal to Z2, there is no elevation difference. This pipe is horizontal. So Z1 equal to Z2, that is Z2 minus Z1 or Z1 minus Z2 equal to 0. So just rearrange, take together P1 by rho 1 g term and P2 divided by rho 2 g term. So P1 by rho 1 g ln of P1 minus P2 divided by rho 2 g ln of P2 equal to V2 square minus V1 square divided by 2g, as Z1 equal to Z2 equal to 0. But for isothermal process, I already used this expression P1 by rho 1 equal to P2 by rho 2. So just in place of P1 by rho 1 or in place of P2 by rho 1, you can substitute P1 by rho 1 or P2 by rho 2. So for your convenience, I'll substitute in place of P2 by rho 2, I'll substitute P1 by rho 1. So P1 by rho 1 g can be taken out. So P1 divided by rho 1 g into ln of P1 minus P2, as ln of P1 minus ln of P2 is ln of P1 by P2 from the rule ln of A minus ln of B equal to ln of A by B. So P1 divided by rho 1 g into ln of P1 divided by P2 equal to V2 square minus V1 square divided by 2g. So now P1 divided by rho 1 g I'll keep as it is into ln of 40.3 into 10 to the power 4 divided by 30.3 into 10 to the power 4 as pressure values are given. So equal to V2, we already got expression V2 equal to 5.32 V1. Just substitute 5.32 V1 to the power 2 minus V1 square divided by 2g. So just simplify P1 divided by rho 1 g. So ln of 1.33 equal to 27.30 V1 square divided by 2g. Now divide entire expression by g. So P1 divided by rho 1 into 0.285, that is the value of ln of 1.33 equal to 27.30 V1 square divided by 2. So P1 divided by rho 1 equal to 47.894 V1 square, just upon simplification. So P1 by rho 1, but from equation of state we have P1 by rho 1 equal to RT1. We know the values of R and T1. Just substitute R value as 287.14 and T value as 277 and get value of P1 by rho 1. So that is equal to 79537.4. So just substitute P1 by rho 1 in above expression in order to get V1. So we get 79,537.4 equal to 47.894 V1 square. So upon taking square root, we get V1 equal to 40.75 meter per second. So when you get value of V1, we can easily get value of V2. That is just because V2 equal to 5.32 V1. So just substitute in place of V1 40.75. So V2 we get 5.32 into 40.75, that is equal to 216.71. Those are the two values V1 and V2 we are supposed to find. So that is the answer. Now let us go for last problem. A gas with a velocity of 300 meter per second is flowing through a horizontal pipe at a section where a pressure is 6 into 10 to the power 4 Newton per meter square absolute and temperature is 48 degrees centigrade. The pipe changes in diameter and this section the pressure is 9 into 10 to the power 4 Newton per meter square. Find the velocity of the gas at this section if the flow of gas is adiabatic. This term is very important. This is for adiabatic process. So whatever the problem we have solved before, that is actually for isothermal process. This is a somewhat different problem. We have to know expression for adiabatic process. Okay, let us write down the data. So gas with a velocity of 300 meter per second is flowing through a horizontal pipe at a section 1,1. That means V1 is given as 300 meter per second and horizontal pipe. This is a case of, there's like two types of case. One is horizontal pipe, other one is inclined pipe. Horizontal pipe, we have values Z1 equal to Z2 equal to same value. So Z1 minus Z2 or Z2 minus Z1 equal to 0. For inclined pipe, we have some definite value Z1 minus Z2 or Z2 minus Z1. That like values of Z1 and Z2 will be given in problem. So here no need to get confused. So here's a horizontal pipe Z1 equal to Z2. So where section 1,1, the pressure is 6 into 10 to the power 4 Newton per meter square. There is an absolute. P1 is given as 6 into 10 to the power 4 Newton per meter square. You can see the unit of pressure. It is not Newton per centimeter square. So it is very easy. You can directly take down the pressure. It is already given in SI unit. There is Newton per meter square. And again, one more important thing. Pressure is given in absolute pressure. So this is a total pressure. So no need of converting the given pressure to absolute pressure by adding atmospheric pressure. So it is already in absolute pressure, and temperature is 40 degrees centigrade. So T1 is 40 degrees centigrade. You are supposed to convert to Kelvin. The pipe changes in diameter, and this section the pressure is 9 into 10 to the power 4 Newton per meter square. That's P2 is 9 into 10 to the power 4 Newton per meter square. There is again absolute pressure, so no need of conversion here also. Find the velocity of the gas at this section if the flow of this gas is adiabatic. So you have to find out the velocity, that is V1 is given as 300 meter per second. You are supposed to find V2 value here. Okay, let us just write down the data things. So at section 1 and section 2 you can write side by side in order to compare. That will be very easy. So V1 is given as 100 meter per second. T1, that is equal to 6 into 10 to the power 4 Newton per meter square. T1, this is small letter T1 for degree centigrade. T1 equal to 40 degrees centigrade. Just convert from degree centigrade to Kelvin. So that is T1 equal to 273 plus 40 equal to 313 Kelvin. And at section 2, P2 equal to 9 into 10 to the power 4 Newton per meter square. There is absolute pressure. No need of converting to absolute pressure again. Then V2 are supposed to find R value, that is the gas constant that is given in problem, that is equal to 287 joule per kg Kelvin. Again you can see the difference here. In previous problem it was given in Newton meter kg per kg Kelvin. So Newton meter is similar to joule. So 287 joule per kg Kelvin. No conversion here also. So adiabatic flow, to assume for adiabatic flow K equal to gamma equal to 1.4 isentropic process. So as I already told, the gamma is ratio of specific heat. So instead of gamma here they are using K. So you can use any value instead of gamma. You can go for K or any definite value, but definite symbol, but you have to specify that is like K is ratio of specific heat. Now we have Bernoulli's equation for adiabatic process as section 1 and 2. Now I am going to use K as a symbol for ratio of specific heat. So K by K minus 1 P1 by rho 1 G plus V1 square divided by 2G equal to K by K minus 1 P2 divided by rho 2G plus V2 square divided by 2G. Actually I didn't write Z1 and Z2 term because it's a horizontal pipe. Z1 equal to Z2, so Z1 minus Z2 or Z2 minus Z1 equal to 0. So I wrote directly that expression there, and that expression whatever I have written there, that was written there was obtained for the adiabatic process. I already derived that expression. So you can combine together similar to isothermal process, combine together P1 by rho 1 G term and P2 divided by rho 2 G term, that is a pressure head. So K by K minus 1 into P1 divided by rho 1 G minus P2 by rho 2 G equal to V2 square minus V1 square divided by 2G. Just divide entire expression by G. So K by K minus 1 into P1 by rho 1 minus P2 by rho 2 equal to V2 square minus V1 square by 2. Now you can just rearrange the expression by taking P1 by rho 1 outside the bracket. So K by K minus 1 into P1 by rho 1. So when you are going to take P1 by rho 1 from first term, that becomes 1. So into 1 minus P2 by rho 2 into rho 1 divided by P1. That is equal to V2 square minus V1 squared by 2. Take that expression as 1. But for adiabatic flow, we know that is P by rho K equal to constant. So you can apply for two state points. So that's 1 and 2. P1 divided by rho 1 k, rho 1 to the power k equal to P2 divided by rho 2 to the power k equal to constant. So just get expression for P1 by P2. So P1 by P2 equal to rho 1 by rho 2 to the power k. So from that you can get expression for rho 1 by rho 2 by taking the power 1 by k. So rho 1 by rho 2 equal to P1 by P2 to the power 1 by k. That take that expression as 2. Now you can back substitute rho 1 by rho 2 in equation 1 in place of rho 1 by rho 2. So k by k minus 1 into P1 by rho 1 into 1 minus P2 by P1 into P1 divided by P2 to the power 1 by k equal to V2 squared minus V1 squared divided by 2. So you can just substitute the values of k, P2, P1 and V1 value. So upon substituting we get 1.4 divided by 1.4 minus 1 into P1 divided by rho 1, keep P1 and rho 1 term as it is, explain about that thing later, into 1 minus 9 into 10 to the power 4, there is a pressure, P1 pressure, divided by 6 into 10 to the power 4, P2 pressure, into 6 into 10 to the power 4 divided by 9 into 10 to the power 4 to the power 1 by 1.4. This 1.4 is very important. You have to assume nowhere it will be given in problem. So for adiabatic flow, gamma should be taken as 1.4 or k should be taken as 1.4. That is equal to V2 square minus V1 square divided by 2g. So just simplify, that is 1.4 divided by 1.4 minus 1, that becomes 3.5. 3.5 into P1 by rho 1 into, just simplify the bracket term, we get 1 minus 1.1228 equal to V2 square minus V1 square by 2. So upon simplification, 3.5 divided by P1 rho 1 into 1 minus 1.1228 equal to V2 square minus V1 square divided by 2. Now we know the value of V1, just substitute and simplify the bracket terms. So upon simplifying bracket terms and multiplying by 3.5, we get minus 0.4298 P1 by rho 1 equal to V2 square minus 100 square divided by 2. But from equation of state, you can use equation of state for any point, either the even though a given process is adiabatic, isothermal or polytropic process, we can use anywhere. So but from equation of state, P1 by rho 1 equal to RT1. So P1 by rho 1, so equal to RT1, R value is given. So R value is 287 and T1, that is 313. That is the temperature in Kelvin, equal to 89831. Just multiply 287 into 318. Then you can substitute this value of P1 by rho 1 in previous expression, that is minus 0.4298 P1 by rho 1 equal to V2 square minus 100 square by 2. So we can just replace P1 by rho 1 as 89831. So minus 0.4298 into 89831 equal to V2 square minus 100 square by 2. So just multiply 2 to the other side, that is 2 into minus 0.4298 into 89831 and add plus 100 square and take square root of that value. So we get V2 equal to 113.0 meter per second. So these here only 3 problems are there, but those are the 3 problems are very important. 2 problems on isothermal process and last problem on adiabatic process. But don't forget students, here you don't forget to convert from Newton per centimeter square to Newton meter square, and again SI unit you should be very careful in solving the problem. If you are going to substitute directly in CGS unit, that is Newton per centimeter square, you are going to end up with wrong answer. So that should be careful while solving the problem. So this is a very easy problem. Even I gave the same problem for assignment. You can just refer assignment problems, or you can refer to that compressible flow PDF, whatever I have shared in Google Classroom. So, and you can again refer to Google Classroom folder. You can get materials for fluid mechanics module 1, module 2, module 3, 4 and 5. And again I attached fluid mechanics CBCS question paper along with 10 and 6th scheme. You can just refer to Google folder and you can download and you can start studying from that question paper itself. So thank you.